I'm just preparing the live stream.
Nirjala, so you are from Himachal Pradesh, am I correct?
Good evening, sir. Yes, sir.
Yeah, okay. You are doing MSc, right?
Yes, sir.
Okay. Oh, Priyanka also joined. Priyanka Aroda.
Hello, sir.
Hi, hi.
Yeah, hello, sir.
Yeah, nice to see you.
Hello.
How are you, sir?
Hi, hi. Ah, fine, fine, good. So you are in which year now?
Sir, fourth year.
Fourth year, okay.
It's been quite a while since we saw her.
Ah, yeah, yeah. So can we start then?
Yeah, I think we can start.
So, Chaitanya, I will start.
Yeah.
Yeah. So, uh, welcome to all. Today is the fourth edition of the PTMT days, and today topic is stochastic matrix. And our today's speaker is Professor Satyanarayana Reddy. He is currently associate professor in Shivnadar University, Institute of Enemy, Delhi NCR, and he is also a faculty member in the MTTS Trust, and he's taken so many lectures in summer camps in real analysis, number theory, and many more. And he's also taken so many conference lecture and his specialization in the number theory. And I welcome to you, sir. Please
Yeah.
take.
Yeah, okay. Thank you, Franshu. Good evening to all of you. I am very thankful for giving this opportunity. So it is a PTMT day, right? So I'm not a PTMT participant, but okay. But even then, so they invited me. Right. So since it is PTMT day, so this is actually related to how to introduce a concept, not giving a lot of uh, things about the double stochastic matrices. I'm just introducing the concept, right? Yeah. So, uh, so there is lots of questions will be there. So I hope participants will respond to them, right? So it is not covering some content. It is just introducing something. Okay. So before going to start, double stochastic matrix, I'll going to start in 5 minutes or so. But before that, I just introduce something, right? Yeah. Okay. So so this is a graph. Okay, we'll say it is a graph. Graph means collection of vertices and edges, right? So here, what are the vertices? 1, 2, 3, A, B, C, D are the vertices, and there are edges between them. So there is an edge between 1 and A. There is an edge between A, B, 2C, 3D, like that. Okay. Yeah. Okay. So this is a called graph. Okay. Now here edge meaning that it is also a set. Okay. For example, 1A is an edge. We can think that edge as a set with two vertices because there is an edge from it is edge between A and 1. There is no direction. So we'll denote it as a set. Okay, set with two elements. Hope you understand what is a graph, what are the vertices, what are the edges, right? Now I'm going to define something. A simple graph means no self loops and no parallel edges. Okay, so X is a simple graph. Then matching in a graph is set of edges which do not share any endpoints. Okay, I'll explain you further. A set of edges without common vertices. Okay, yeah. So the vertices incident to the edges of a matching, say M, okay, are said to be saturated by M. Okay. So M is capital M is set of edges. The each edge has end vertices, right? Those those vertices which are end vertices of edges in M are called saturated by M. Okay. Other vertices are unsaturated by M. Okay. So perfect matching. A matching is said to be perfect matching means a set of edges is said to be perfect matching. It saturates every vertex. Okay. So this is the definition. So I'll say further, a matching M is a subset of E. Again, I'm revising one more time. First of all, a matching is a subset of the edge set. Okay, hence set of sets. Okay, each element M is an edge, hence it is a set with two elements. For example, E1 equal to AB, E2 equal to CD. These are two edges, right? Then, so there are elements in M. M is a matching. So there are no end vertices. So E1 intersection need to become empty set. Okay, a vertex V is saturated by M if there exists a edge in M such that B belongs to E, right? Yeah, okay, right. Okay, and M is a perfect matching if my vertex set V is equal to union of all these edges which are in M. Okay, each edge is actually a set, right? Set with two elements, so their union equal to the whole of V, then it is a perfect match. So are there any questions? If there are no questions, can you tick yes? You know how to tick yes? Okay, good. Fine. Okay, if not clear also, don't worry. I'm giving example now, right? Yeah. So look at this graph, right? So what do you say about 2B is an edge and 3D is an edge, right? Is it a matching? Is anyone, anyone, can you tick yes if it is a matching or not? Is it a matching? What do you mean by matching? The edges do not have a common end vertices. What are the common end vertices of edge 2B, 2 and B, right? The end vertices of edge 3D is 3 comma D. So they are not common, right? So it is a matching. Okay, anyhow, I'll tell you clearly now. Look at this. Okay, the following are matchings. M1, 2B, 3D is a matching. Okay, and is it possible to add one more edge to this? Is anyone want to comment? Is it possible to add one more edge to this? Still, that is a matching. Unmute and say, no problem.
So 1A?
1A, correct, very wonderful, correct. 1A can be added, right? Still 1A can be added and that is also a matching, correct? Yeah, okay. Now M3, you see that AB and 2, 3, that is also a matching. Is it possible to add one more edge to it? Is it possible to add one more edge to it? You cannot add, right? Are you understanding? Yeah, we cannot add because AB is there, then I cannot add B2, right? And 2, 3 is there, I cannot add 2C or 3D, right? So these are, there is some concept called maximum matching, maximal matchings and different things, okay? Yeah, so this is also a matching, right? Yeah. So you understand what is matching means. Is this graph has a perfect matching? If not, why? Is anyone want to comment on that? Perfect matching means what? The edges has to cover all the vertices. For example, if you look at M2, right? M2 is covering 1, 2, 3, A, B, D, but it missing C, right? So it is not perfect matching, right? Yeah, is it that is not a perfect matching, but can you give a perfect matching? Any one of you, another matching which saturates all the vertices? Is it possible? Anyone? You want to comment? Okay, just small hint. How many vertices are there total? How many vertices are there?
7. So if we
Seven.
remove C, I think it becomes.
Yeah, when you have a perfect matching, then I need to do 2 vertices, right? So 7 vertices, I cannot have a perfect matching. So necessary condition to have a perfect matching is that first it need to have even number of vertices. Hope it is clear. Okay, so now we can talk about more about matchings, right? So just empty set is also a matching because the condition is that the edges which you collected do not have common end vertices. But generally we'll consider non-empty sets only. Any single edge is always matching. The goal is to find matching with maximum number of elements. Usually that is the goal in matching theory. Okay, it has lots of applications, right? So I'm asking several questions here, but I'll move forward. This is not our main goal, right? Yeah. So can you see this? So this graph is a cycle graph. Okay, cycle graph means that the vertices all form a cycle. A, B, C, D, F, and A. Again, come back to A, right? So this is the cycle of length 6. So we'll denote it by C6. Are you able to understand that AB, CD, EF is a perfect matching? Do you agree? Any one of you? Do you agree that is a perfect matching? Yeah, so okay. Yeah, it is a perfect matching. The reason is that all vertices are exhausted, right? A is a B, C, D, all vertices are exhausted. This is another perfect match. B, C, D, E, and okay. So we have perfect matchings here, right? Yeah, okay. Now look at this thing. So this graph is not only just a graph, it has some other thing. These graphs are called bipartite graphs. Bipartite graph means that vertices are divided into two sets. Okay, I hope it is clear from the picture. A, B are two. Their union equal to the set of all vertices, right? And you see that there, if you take any edge, one end vertex is in A, one other end vertex is in B. Vertices in A, there is no edge between among them, right? So this type of graphs are called bipartite graphs. Hope it is clear to you. Okay, yeah. Okay, bipartite graph is a graph only, but here vertex is divided into two sets. Okay, their union V is equal to union of two sets, such that every edge you take, one end vertex is in A, other end vertex is in B. Okay, now you take S is a subset of V. Actually, you can take S is a subset of V, meaning including A and B. But here I am collecting only subsets of A only here, right? Yeah. First of all, what is a neighborhood of S? All those vertices such that there is an edge from, there is one more vertex in U in S, that U comma V is an edge. Neighborhood of S is all vertices. Neighborhood of S, right? Neighborhood of S. For example, if I take X1, the neighborhood is Y1 and Y2. These are the edges adjacent to that. Okay. So that's what I written here. You can understand it easily. S equal to singleton X1, the neighborhood of S equal to Y1, Y2. S is equal to X2, the neighborhood is Y1, Y2, Y3. Yeah. So is it clear to all of you? Can you tick yes if you are clear with what is S and the neighborhood of S? Yeah, it is because I'm asking, sorry, we are not writing. I'm prepared slides. Okay. Actually, we have not do that, but this time I'm doing that. Yeah. Okay. Only 1%, 8 people. Okay, good. Nice. Okay, nice. It is clear to you. Okay. What is observation here? You can see that S is subset of A, then the cardinality of S is less than or equal to cardinality of the neighborhood. Okay. I hope it is clear to all of you, right? You take any S here, non-empty set. If it is S is empty, then obviously equal to will happen, right? Okay. So every you take any subset S of A, then the cardinality of S is less than or equal to cardinality of its neighborhood. That is what is happening in this graph. Okay. Yeah. Now let us look at this graph. Okay. So where matchings will come. Okay. So sometimes boys and girls, right? Marriage issue, right? Sometimes this side we have people, that side we have jobs, right? We need to match person to jobs like that. So bipartite graphs are comes with me several places. Okay. Now can you tell me that I hope you understand the graph, right? Boy B1, boys are B1, B2, B3, B4, girls are G1, G2, G3, G4, right? Every edge in this graph, one end vertex is in B and other end vertex is in G, right? There is no edge between the boys. So so it is constructed like this. Boys boy B1 knows girls G1 and G2, knowing only. They know or they interacted before. Okay, then we'll put edges. Okay, there are no edges between the boys, even though they know it is only between boys and girls. Because boy are willing to marry the girls whom they know already. Okay, so what are the choices for B1? Whom B1 can marry? B1 is willing to marry only which girls? Anyone?
G1, G2.
B1, B2 only, right? G1, G2 only, right? Yeah, okay. So that is the way. So now the question is that is it possible that every boy will be married? Is it possible here? Anyone can comment on that?
No,
No, it is not possible. Why?
because there are 4 boys and only 3 girls.
Yeah, they know each other, right? That means that this set S is a subset of A. Neighborhood is less than or equal to S, right? In the previous example, we saw that whatever the set S you take, okay, that cardinality of S is less than or equal to cardinality of N of S. But in this case, it is not happening like that. In that case, some vertices here are not matched. Okay, so this is the thing. This is called Hall's condition. Of course, this he expressed in by using set. There is something called um, some other area, other topic called system system of distinct representatives. He not stated in this version, but this is this is a version of Hall's condition in terms of the graph theory. Okay, what is this? First, I'm defining what is a Hall's condition. Okay, so bipartite graph, if you take with bipartition A and B, we say that X satisfies Hall's condition if for every subset S of A, neighborhood of S, that set cardinality is more than the set S. Okay, in this case, we'll say that that graph satisfies the Hall's condition. Graph is satisfying the Hall's condition. A graph satisfies Hall's condition if you take any subset S of A, cardinality of S is less than or equal to cardinality of its neighborhood. Okay, and there is a nice result. Without proof, I am stating. If time permits, I'll prove also. Okay, so a bipartite graph we have. Okay, then there exists a matching. Matching, you remember that it is a collection of edges, right? No end vertices common. So every vertex, so there exists a matching. Every vertex in A, okay, every vertex in A has a distinct matches to distinct vertex in B. Okay, this if and only if Hall's condition is satisfied. You see that in the previous slide, Hall's condition is not satisfied. There is a set whose cardinality is less than or equal. It is greater than or equal to the cardinality of N of S. Right. That's why it is not possible. But it is a if and only if condition. So every vertex A will be saturated if and only if it satisfies the Hall's condition. Okay. Yeah. So this is the background. Now I hope many students, many participants joined. Now I am going to the actual topic. Okay. Now I will go as per our usual way, asking more questions and all. Okay. So are there any? Yeah, Priyanka, please go ahead.
Sir, so can we say that like if we take the connected graph, connected rotate graph,
Hmm.
then it will.
A connected graph also it may not happen. Okay. Yeah, bad luck in the last example, it is disconnected G4.
Yeah.
Even I can give examples, even the graph is connected also. With the graph is connected, but this condition may not satisfy. If it is not satisfied, then A cannot be matched, right? Yeah.
Okay.
Yeah. Okay. Thank you. Yeah. Any other questions? Okay.
So I have one question.
Yeah. Yes, please.
So
Yeah,
in
please.
the previous slide, you mentioned that the number of elements in N of S will always be greater than or equal to the number of elements in S for all S, every subset.
Yeah.
So that Hall condition is true for any graph.
No, that is not true. If it is true, then why will say? We say that a graph satisfies Hall's condition if this condition is satisfied, right? So there exists S. subset of A. So Hall's condition not satisfied meaning what? There exists at least one set which is subset of A, such that the cardinality of S is greater than n of S, right? Yeah. So all graphs will not satisfy this. Okay. Yeah.
Got
So
it.
sorry, I'm not giving more examples. Anyhow, this example already there. Here, B1, B2, B3, B4 is a, we can take it as S. That means my set S itself is equal to entire A, right? So then S contains 4 elements, but neighborhood of S contains only 3 elements, G1, G2, G3. So there exists S, right? But if you take only B1, B2, you see that B1, B2 as my set S, right? Then what is the neighborhood of S? That is G1, G2, G3, correct? There it is true. So it is Hall's condition not true means at least there exists at least one set S, subset of A. We have entire B1, B2, B3, B4. Hope I am clear. Okay. I hope you understood. Yeah, I'll move forward. Now actually coming to the topic. Okay, now your turn now, not me. Okay, we will use that whatever we introduce later. Now fresh. We'll start from now onwards. Yeah. So observe this matrix and tell me whatever you notice, whatever it may be. Can you say few observations? For example, I'm telling you.
1 is an eigenvalue.
Sorry. Yeah.
1 is an eigenvalue.
Okay, that is very big. Okay. So
The
we'll come
sum
to
of every row and column is equal to 1.
yeah, each row sum is 1, each column sum is 1. Any other?
Symmetric.
In this example, it is symmetric also, but in general, yeah, okay. I am asked here, you are correct. It is symmetric. All row sums are 1, all column sums are 1. And one of you told that even 1 is an eigenvalue. That we will see in a while. Why
Entries
it is
are rational.
entries are?
Rationals.
Here it is rationals. Yeah, good.
Positive entries are non-negative.
Non-negative. Yeah, that is what I am looking. The entries are non-negative. And rational, so they are real numbers, right? Yeah. So that is the question. All entries are non-negative. That means given any ij, aij greater than or equal to 0. Yeah, sum of the entries of the row is 1. That is j is equal to 0 to 3, aij equal to 1. Correct? Sum of the entries of the columns is 1. That means I is equal to 0 to 3, aij equal to 1. Correct? Yeah, this is true for every j. Hope you know that. You hope it is clear to you. So these are the main 3 conditions. Okay, to make it, it is a doubly stochastic matrix. I'm not defined it. Yeah. So since title, you know, title of the talk. Yeah, one of you told very nicely. So what is this 1 1 1 1 vector if I multiply to this column vector? What happens if I multiply 1 1 1 vector to this? In general, you take any square matrix, right? You multiply 1 1 1 vector. What you get? Let us take a 2 by 2. A11, A12, A21, A22, right? You multiply 1 1, 1 1 vector. What you get? A11, A12 into 1 1, right? Dot product of the first
Sum
row.
of rows.
Sum
Sum
of
of, yes, wonderful. We'll get sum of rows, right? That is in general for any matrix, it is true. When you multiply 1 1 1, it is very nice. Please practice that. 1 0 0 if you do, you'll get the first column, right? 0 1 0 0, you'll get the second column. Like that, 1 1 1 you take, then I'll get the row sum. Wonderful. Okay. Now, what is that row sum? Each row sum is 1. Okay. Then what is that AE3 now? What is AE3? E3 means 1 1 1, right? What is AE3? Again E3. So then what is the conclusion from that? AE3 equal to E3 means?
E3 is an eigenvector.
With eigenvalue?
1.
1, right? Yeah, beauty, right? So always now I already know that there is one eigenvector. And what about what about this? Okay. What about this? E3 transpose into A means row vector if I multiply. That gives the
We
columns.
get the
Right?
columns.
Yeah. Okay. What
It
about
is
this
also
thing?
1.
Yeah, that is also 1. That is row eigenvector, column eigenvectors like that. But anyhow, that's what is E3 transpose AE3? You know X transpose AX we do, right? Finally, what is the size of this matrix? E3 transpose AE3. What is the size of the answer is 3. Wonderful. Yeah, one of you already told, so I'll continuing. You are told the answer is 3. What is 3? Right?
1 cross 1 matrix.
That matrix is 1 cross 1. What is that number 3 she told? One of you told. Because what is E3 transpose E3 is doing? In general, if you take any matrix, what is this do?
Sums the entries, all the entries of.
Sum of all the entries. Beautiful. Sum of all the entries. You see that is the size of the matrix. Okay, good. Okay, so without actually I'm defined, we have several properties of this. So it is clear that is an eigenvector with an eigenvalue 1. Okay, now I'm defining actually, right? A non-negative real matrix. Non-negative matrix means entries are non-negative and real numbers. Is said to be doubly stochastic. If sum of the elements in each row and sum of the elements in each column is a 1. Okay, so how you define it? So in general, right? So we already done. So this is the thing. Okay, but I told m cross n. Now the natural question is that is it m equal to n? These are the questions. Yeah, that is the question. Is A has to be a square matrix? You know, when you define symmetric matrix, we'll say that A equal to A transpose, right? Right. Then we can prove that actually A is a square matrix, right? In the definition, we do not ask it is a square matrix, right? But we'll prove later it is a square matrix, correct? Similarly, somebody can prove that? Is it a square matrix first or not? Is it m equal to n or not? Can we prove that? Is the question clear? Anyone? Okay, at least what is your guess? What you feel? Conjecture. Okay, let us see. So, yes, actually, it is a square matrix. How do you show? Some of the elements of A is all the elements of A is n, right? It is an n cross m. You already noticed. It is also m. Why? Why some of the elements is n? Because row sums, you know that column sums are 1, right? Each column sum is 1, correct? So how many columns are there? N columns are there, right? If I sum all the elements, I'll get n. Are you okay? Can you take guess? Is it clear?
Yes.
Yeah. So similarly, row sums are also, each row sum is 1, right? How many rows are there? M rows are there, right? But that is entire sum of all the elements. You first sum the rows and then sum the row sums, or first sum the columns and again sum all the column sums. We'll get the same answer. It is called two-way counting. In combinatorics, it's frequently used. Two-way counting. Okay. Hope you are understood this. Yeah. Any questions? Is it okay? Okay. So I'll proceed then. Yeah. So another way, nice way. Okay. Prove or compute the following. So nice thing is that I'll introduce the matrix J, like identity matrix, right? So J denote the matrix with all entries are 1. All the entries are 1. Okay, 1, 1, 1, 1, 1, 1 like that. Now this is actually depending upon the context, right? J size of J is same as A. Okay, I hope you understand from the context. No need to specify what is the size. Okay. So you know that identity matrix. Okay, everyone know. Then the matrix multiplication identity. If you multiply, I'll get the same. Actually, there is one type of product called, see, in mathematics, in matrix theory in particular, when you add two matrices, we'll add component wise. When you subtract also, you do component wise. Suddenly multiplication, you take row and column, right? Suddenly something comes, right? But actually, if you ask student without defining, how do you multiply? Usually. So if you give, then he will try to multiply component wise only. Okay, if the matrix sizes are same, you can multiply component wise. In that case, this J matrix become identity for that. Hope you are clear about. J matrix also plays an important role, right? Yeah. So so a non-negative matrix is DSM if and only if AJ equal to JA equal to J. Is it okay? But here I am telling that already non-negative matrix. Three conditions, na? Given matrix is DSM or not, we need to ask three more questions. What are the three questions? All entries are non-negative or not? Each row sum is 1. Each column sum is 1 or not, right? These are the three conditions. I already told it is non-negative. But now if and only we are saying, is it easy to see this proof? What do you mean by AJ? Right? Each column is a 111 vector, right? We already noticed AE3 is equal to 1 times E3, right? Hope you understood that. So AJ equal to J only we get. Right. So it is easy. This proof is easy. Am I okay or not okay? I'm a little fast. Please let me know. If it is okay, can you take yes, please? I'll wait for some time.
Sir, for the converse part, whether the only possible matrix A is the identity matrix?
Converse, actually, AJ equal to J equal to, we are multi, it is, yeah, what is, can you repeat that?
I mean, my point is for the converse part, if AJ equal to J, then whether the only possible A is the identity matrix, and that's why it is doubly stochastic.
No. First of all, see, please understand that I'm now concentrating only on non-negative matrices, right? Identity matrix is also a identity matrix. See, in identity matrix, what I will get? I will not get A. I will get A, not J, right? Ij equal to J, I is equal to. There also I'll get J. That's correct, right? That's correct because identity matrix also doubly stochastic. Am I correct?
No, yes, sir.
Yeah.
Setta, may I just comment?
Yeah. Yeah.
Okay. I mean, you forget about this all one n by n matrix, or I mean, so you just consider one. I mean that what it called all one row, all one column.
Column. Yeah.
Okay. So if someone writes okay A times all one column, what you get? You'll get all one column. So essentially, it means that your row sum is 1. Now you duplicate that n times. Okay, each column you multiply 2a, so I'll get 1, 1, 1. So each column multiply 2, so finally I'll get j only. Now when you talk about ja, each row of j you multiply 2a, so you'll get all one row. So you are not going to get an identity matrix here. Is it clear?
Yes, sir.
Yeah, actually, he is thinking that the converse part only true for.
No, that's what. So yeah. I mean, if so, that is also if and only if. Right. So A all one matrix, all one column is equal to 1 all one column means your row sums are 1. Okay. Yeah. So therefore, it is not identity matrix, but rather it says that your row sums are all 1, column sums are all 1. And why it is taken J all, I mean n by n square matrix, why it is taken? Okay, so that it works both ways. Otherwise, you have to take columns towards the right side or rows towards the left side. Now, if it is all 1, you duplicate it 10 times, columns or rows. Okay, so that will give.
Okay.
Yeah.
So
sorry.
Yeah, thank you, sir. Okay, so this is sometimes it is in handy, right? If and only if conditions are useful for us, right? Instead of definition, sometimes we'll use proofs. Maybe becomes easy by using this sometimes, right? Yeah. Okay. So is it true that if A is DSM, A transpose is also DSM? How many of you agree or not agree? If you are agree, can you take yes? If A is DSM, A transpose is also DSM. What are the conditions we need to check? one way to check is that, yeah, so is it non-negative again? Yes. A is non-negative, A transpose is also non-negative, entries are non-negative. Yeah, but otherwise you can look at the previous if or no if condition, you can take transpose on both sides, easy to see. J is already symmetric. Otherwise also easy to check, row sums wise also. By definition also not tough. Okay, can you construct a 2 by 2 DSM? Now I'm clearing. So can somebody think about and tell me? So can you give me one 2 by 2 double stochastic matrix? Are you able to give one? Okay.
All half matrix.
Right. Half, 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 half. Right. Correct. That is a double stochastic matrix. Any other person? Second, any other person? Can you give me one more?
Identity.
Identity. Wonderful. Good. Right. Yeah. So you understood. Okay. So just I'm asked one double stochastic. You gave. Good. Nice. So can you construct a 3 by 3 double stochastic? Yes. Now all that you done can be extended also, right? 1 by 3, 1 by 3, 1 by 3, all 1 by 3 will work and identity will work. Any other? Somebody can give me different one other than these two? Just
permutation matrices.
Permutation matrices. Okay, good. So we'll discuss those, okay, as time progress. Yeah. Okay, so good. So is it true that if you know n minus 1 square, n minus 1 whole square entries of n cross n double stochastic matrix, right? Then is it is possible to compute the remaining entries? Okay. Yeah. So I'm not discussing it. You can think about this problem. Easy only, right? Yeah. First of all, is it true for n is equal to 2, right? Okay. To make you understand, what happens if I take n is equal to 2? N equal to 2, then n minus 1 whole square. Only one entry. If I know one entry, can I know all the entries of double stochastic? Like that. Okay. So if I know, if I take a 3 by 3 matrix, if I know 4 entries, can I know all the entries? These are the things. For n equal to 2, it may be true. Okay. N equal to 3, you need to think about. Okay. But if I give a particular position, it may be true. Okay. So I'm not going into details. Easy problem only. Right. Yeah. Yeah. Is a product of 2 DSM is a DSM? I made as a statement. So, so it is true. So can somebody prove it? How to prove that?
So
We
we
can
can
use
use the
the first
condition first.
criteria.
Okay. First of all, again, we need to ask 3 questions, right? What is the first question? First question is that is the product of 2 non-negative matrix again non-negative? That is true. No issue. Now you are right, correctly pointed out first criteria. So AB into J. Here you see the beauty. AB into J is actually BJ, right? BJ is J. Like that, you can use this result very easily and we can get, right? Otherwise, it will complicated to usually by definition, it is little tougher. Yeah. So very nice. Thank you. So you figured out. Yeah. Hint, use the first result. You already told. I want to give hint, but you already told. Yeah. I hope all of you clear about this. Yeah. Okay. So product of 2 DSM is DSM. Can you tick yes if you are clear or if you are clear, please? Okay. Good. Nice. Wonderful. Okay. So we'll proceed then. Okay. Yeah. So what about the convex combination of 2 DSMs? Okay. Before going to that, so product of 2 DSM is DSM, right? And you already know that associative property anyhow hold for matrices. And do you know any identity matrix? So if I collect all double stochastic matrices, right? If I collect all double stochastic matrices, is it to form something? I am not telling you. Is it forms a group or is it forms a something? Any comment you want to make. If you know, that's okay.
So maybe under multiplication.
under multiplication, usual multiplication, you already proved that the product of two doubly stochastic is doubly stochastic. So, like you say, closure property that is there, right? Associative anyhow there. What is identity? What is identity element? Identity matrix itself. That is also doubly stochastic. So that is anyhow multiply. I'll get the same matrix, right? All of them are there. But what about inverse? Right? Even you told 1 by 2, 1 by 2, 1 by 2, 1 by 2. Is it inverse exist for that? No, right? Yeah. So it is a monoid at most. Okay, like that. So my goal is that today asking questions only, right? So how in it when you as a teacher, how do you ask more and more questions? Okay, so that students will get confidence about the concept. Okay, what is a convex combination? Okay, so convex combination is that like a linear combination, but in the convex combination, the coefficients will sum up to 1 and they are non-negative again. Okay, then that is called a convex combination. Is a convex combination of DSM is a DSM. So I gave the proof below. Okay, not giving time to you. But without look at that, you can think about also, right? Yeah. So if A and B are belong to omega of n is actually now next is that actually omega n is set of all. If you denote set of all doubly stochastic matrices by omega of n, right? That is what is the definition? Mn of r aj greater than or equal to 0 and aj equal to j a equal to I, j, right? So otherwise that is little complicated to write. Sum is some summation I is equal to 1 to n row sum equal to 1 column sum equal. That is the definition, but it is easy to specify here, right? Yeah, okay. Now, so is it a convex combination of DSM is DSM? That is a question, right? So we'll work for two matrices. I take A and B, right? Convex combination. So lambda A plus 1 minus lambda A into B. Is it also a double stochastic? That is the question, right? So here lambda is non-negative. So lambda is non-negative and less than or equal to 1 also. Okay. So I'm not specified here, but that is the meaning. Okay. So convex combination means both the coefficients are non-negative. So lambda is lies in between 0 and 1, including 0, right? If lambda is 0, then I'll get B, right? If lambda is 1, I'll get A. They are already double stochastic. But if you take the column sum or the something, you will get it. Otherwise, you multiply with J also, you can check easily. So convex combination of double stochastic is double stochastic. Okay. Yeah, I'm so sorry, I'm not given time to you. I told fully, but I hope it is clear to you, right? Yeah. Okay. So yeah, so just now we have lots of observations about double stochastic. Now we'll go one by one. Can you tell me DSM of order 2? So I gave one entry A. Can you fill up other entries? And what we can say about A? Yeah, these are the questions to you. Anyone comment?
So
A
A
is
has to be less.
between 0 and 1.
A is between 0 and 1. Why that need to be? First of all, it is non-negative, so greater than or equal to 0, I'm clear about. But why you told it is less than or equal to 1?
The sum should be one column and like
Row sum should be 1 and they are non-negative. Already if A is greater than 1, then row sum should be greater than 1, right? Entries are non-negative. Yeah, correct, good. Okay. Okay, what about the remaining entries? Anyone want to comment? Sorry, I'm not giving you to raise hand and all. Yeah, go ahead.
It will be 1 minus A, 1 minus A, and A.
Yeah, right. Okay, good. Hope it is clear. So here, if you know one entry, we know all the entries, right? So every 2 by 2 double stochastic automatically symmetric. In general, double stochastic need not be symmetric, but 2 by 2 is symmetric also, right? See, people will say, but everything we need to observe, right? Yeah, this is I usually say, sir, right? What I learned from Kumaresan sir is that wait for some time. You will observe so many things in it. Still something is there. Yeah. Okay. So, and you already know one is an eigenvalue, right? Can somebody tell me what is the second eigenvalue?
2a minus 1.
2a minus 1. How do you know?
So the sum of the eigenvalues is the trace of the matrix.
Yes, correct. So you already know one eigenvalue is 1, trace is 2a. Then other eigenvalue is 2a minus 1. So you computed all the eigenvalues, right? One eigenvector, you know, 1 is an eigenvector already. You can compute other eigenvector also. I'm not tried here, right? That also you can do it, right? Yeah, good. So it is clear that these two are permutation matrices of order 2. One of you already told permutation matrices, right? So you know, you take a permutation and 1 mapped to 1, 2 mapped to 2, then you can convert that into permutation matrix. 1 mapped to 2, 2 mapped to 1. These are the only two permutation. These are actually doubly stochastic, right? Yeah, okay. So we noticed that product of two DSM is DSM, converse combination of DSM is DSM, right? How to construct the more DSMs, okay? That is the next question, okay? Suppose A is the adjacency matrix of a K regular graph, then 1 by K is a DSM, right? What is that? I'll explain you. You look at this graph. This graph, so there is something called adjacency matrix, okay? So 1, 2, 3, 4, and here columns also 1, 2, 3, 4. If there is an edge between them, I'll put 1, otherwise 0, right? 1, 2, 2, there is an edge, right? I'll put 1, 2, 1, there is no edge, so 0. 1, 2, 2, there is an edge, I'll put 1. 1, 2, 3, there is no edge, 0. 1, 2, 4, 1, right? So you see that each row, how many ones are there? In each row, 2 ones are there. So those graphs are called regular. That is, degree of each vertex is same. That is reflected in the adjacency matrix. Each row sum is 2, right? Each column sum is also 2 because it is symmetric, right? Yeah. So if I divide it by 1 by 2, then I'll get a doubly stochastic matrix, right? Hope it is clear. So similarly this, right? Yeah. So regular graphs will give us, actually there is no difference in both. We can consider as same, okay? We are multiplying just by some scalar, right? Yeah. Okay. So you know this Sudoku. Yeah, please. Yeah, please.
Can you define regular graph?
A graph is regular, the degree of each vertex is same.
Okay.
K regular means the degree of each vertex is K.
Okay.
For example, here, what is the degree of 1? How many?
2.
How many? Here
it's 3.
3, right? All of them are 3.
Yes, got
here,
it.
all of them are 2. Yeah, it is 3 regular, it is 2 regular.
Okay.
That is only exactly I'm dividing by 1 by 3a, 1 by 2a. Right. So this is true for any graph, right? Any K regular graph, I divided by 1 by K, then I'll get the DSM, right? I'm just telling you that how to get DSMs. This is one. You know this? Not you, in general. Anyone? You know this?
Sudoku.
Sudoku, right? In Sudoku, what happens if you row sum is 45, correct? Each row sum is 45, each column sum is 45, correct? If I divided by 45, each entry, then I'll get a double stochastic matrix, right? Yeah. And so then see, now whatever the properties of double stochastic, they will true for here also, correct? So that is advantage. So by studying the DSMs, you will studying indirectly many other. Okay, unknowingly, knowingly, right? Yeah. Okay, that is fine. So now I'll go to there is something called circulant matrices. A matrix is said to be circulant. You rotate the rows, right? First row is A0, A1, AN minus 1. What is the second row? Just shift. Are you understanding that?
Yes, sir.
Yeah. But here I need AI should be greater than or equal to 0. Circulant, it is not, AI should be greater than not required, but non-negative circulant matrices, right? Then what is a row sum? Each row sum is A0 plus A1 plus up to AN minus 1, right? There is a mistake I made. A1 is missing. I'm sorry for that. A0 plus A1 plus A2 up to AN minus 1, right? Yeah. Okay. Yeah. At least we'll do at least one mistake. So that is done already. Yeah. Okay. So now if we divide by that, we'll get double stochastic matrices, right? So this is used actually. You know, in the group theory, we'll make a composition table, right? You understand composition table? Each row, each column are different, correct? But you look at the sums, they are same. Sum meaning element sum, right? So something they are called latent squares. So many different areas. From that we'll get a doubly stochastic matrix. So that is my idea here, right? Yeah. Okay. So here this nice thing is that Wn I'm defining that 0, 1, 0, 0 something. Yeah. So we'll get all eigenvalues. These eigenvalues are very easy, nth roots of unity and all. So I'm not going into this. Yeah. So now each thing need to have some nice result, right? Okay. One of the reason. Okay, I'll tell at the end. Sorry. Yeah. So okay, look at this. If you look at 2 by 2 doubly stochastic matrix, right? What you noticed? A 1 minus A 1 minus A, correct? So it can be written like this: linear combination, convex combination, right? Why it is a convex combination? Because scalar sum is equal to 1 and they are non-negative, right? Already it is DSM, so A is greater than or equal to 0. 1 minus A is also greater than or equal to 0. That means A is lies in between 0 and 1. You already know sum is 1. So every DSM of order 2 is a convex combination of the permutation matrices. Is it okay? Every DSM of order 2, is it okay? That part, can you tick yes? Yeah, okay. Convex combination of the permutation matrices, right? Yeah, good, very good. You understood this. Now look at this example. Now look at this example. Is it a 7 by 12, 5 by 12 row sum? Okay, 12 by 12, 1, right? 1 by 6 plus 1 by 2 plus 1 by 3, 1, right? 1 by 4 plus 1 by 2 plus 1 by 4, 1. Like that, if you do row sum or column sum, it is 1 only. So it is a doubly stochastic. What I done here? What I done here? So I written this as a convex combination of the permutation matrices. Is it okay? You can see that 1 by 4 plus 1 by 4 is 1 by 2, right? So 1 by 6 plus 1 by 2 plus 1 by 3 become 1, right? And these are non-negative. Sum is equal to 1. So what is that I done? Anyone want to comment? Unmute and speak. Can unmute and speak. What we done here? What is my intention? What is in my mind?
To write it as the linear combination of like permutation matrices.
Linear combination of something else. It is linear combination is correct, but it is more than linear combination. More conditions.
Convex linear combination.
Convex linear combination, correct. Okay. So convex linear combination. Okay, thank you. Yeah. So that is exactly this theorem. Okay. Every doubly stochastic matrix is a convex combination of the permutation matrices. Okay. So that is the theorem. Okay. So Kumaresan sir always says, okay, before the proof, we need to understand the statement properly, right? So if you understand the statement properly, then proof also you will get slowly, right? Yeah, okay. So let us, but unravel this, what it is saying. Okay, this is very useful, okay? That is also I learned from MTTS only. When I say linear combination also, we say that one vector is a linear combination of elements of S. Linear combination is always a finite linear combination, right? So first there is an S in natural number. Okay. So this is I learned it from MTTS. First natural number will be there. That many scalars. But here that many non-negative real numbers. Sum is equal to 1. That many permutation matrices. Right? Linear combination also like this only. First one natural number comes. That many scalar, that many vectors. I will write my vector as a linear combination of them, right? So what is the meaning that it is a convex combination is this, right? Such that A is equal to written like this. So this entire result in English, every doubly stochastic matrix is convex combination of permutation matrices. We explained in mathematics. It's a mathematical version. Am I clear about this? Can you tick yes, please? Okay, great. Okay. Okay, so we'll move forward. Okay, so idea of the proof I will give. Later we'll prove much more rigorously. If so, how do you prove this? A is a DSM of order n. Goal is to show that it is some of the convex combination of permutation matrices. If A itself is a permutation matrix, we are done, right? Right? Yeah. A itself is a permutation. I want to write convex combination of permutation matrices. It's 1 into A only, right? If it is not, suppose A is not a permutation matrix, then I'm stating something without proof, okay? But we'll see that. Then there is a permutation matrix P with a property that if Pij equal to 1, whenever Aij greater than 0, okay? Yeah, so I'm making some statement. So whether we'll prove it or not, I'll tell you. We'll prove it actually, right? If A is not a permutation matrix, then there is a permutation matrix P with what property? Okay, when Pij 1, permutation matrix, you know, na, each row in each column we have only 1. Whenever there is a non-zero, at that same location, Aij is greater than 0. Double stochastic matrix have that property. Okay, that is what we are saying. Okay, so suppose we have this, then what we will do? Then we'll take A equal to minimum of these Aij's. See how many ones will be there in the permutation matrix? N places, right? Each row only 1. So entire how many ones will be there? N ones will be there, right? So those N places, Aij's entries are greater than 0, right? Among them, I take the minimum. Okay, then I'll do A minus A small a into P. I subtract A multiplied to P, the smallest minimum value. Then again this matrix become non-negative. Okay, first I ensure that it is non-negative. But now it may not be doubly stochastic. A is doubly stochastic, but this may not be doubly stochastic. So I'll divide it by 1 by 1 minus A. Then this becomes doubly stochastic. Okay. Other thing is that this C has more zeros than A. Are you understanding why C has more zeros than A? Is anyone want to comment? Because we are multiplying AP, right? So one of the entry A, right? In A, capital A, right? Small a is one of the entry. Okay, that we subtracted, right? That big entry becomes 0. I'll give examples, right? Yeah. So then we'll apply induction or something. Yeah. So this is continue the process and we'll get the thing. This is the idea of the proof. I'm not told the actual thing. Okay. Idea of the proof. Sometimes this may be sufficient for some students, right? Yeah. The goal is to show that there is a permutation matrix with the required property. Whatever I stated. So that is the main crux. That comes, then I'll apply this algorithm, I'll get the result. Okay. So, okay, how it is. Now I need to explain this, right? Yeah. Look at this. It is a double stochastic. Already we computed. So I took this permutation matrix, right? Can you see here 1 is there, right? In that place, what is the entry in A? Somebody can comment.
5 by 12.
5 by 12. Here we have 1. In that place, I have 1 by 6 in A, right? Yeah, here I have 1. In this case, I have 1 by 2, right? Yeah. So I choose some permutation matrix such that, okay, whenever it is 1, in the A, it is positive. Okay, that is the way I chose. So P is not unique, right? You can take identity matrix also. Somebody can take this anti-diagonal also. So many, P is not unique. That's why different students may get different ways. Okay, right. Hope it is clear. Actually, if you take a basis, so the combination is unique, but here it is not. Okay. Okay, so fine. So what is the minimum value in 5 by 12, 1 by 6 and 1 by 4? What is the minimum value? 1 by 6, right? Now if I subtract A, multiply this by 1 by 6 and subtract, then automatically it is non-negative. Are you clear about? Can you take yes, please? Yeah, okay. Non-negative only, don't think much, right? Yeah, okay, good. Yeah, so now this B is that. Now see 1 by 6 into that, I will do. This is my B. Now you see that 1 by 6, now that entry becomes 0. Okay, now I divided by this. Now this becomes doubly stochastic. Okay, clearly see the double stochastic matrix with the number of zeros is more than the number of zeros of A. Okay, Now I'm giving the complete picture. How do we prove this result? We prove Birkhoff-von Neumann theorem using strong induction on the number of non-zero entries of A. Further, we use Hall's Maris theorem. We get a perfect matching. Okay. So perfect matching, actually my meaning is that, perfect matching. That means it saturates the A. That provides a permutation matrix. Okay. So that in turn helps us to construct a new double stochastic matrix C with more zeros than A and apply the induction. That's it. Okay. Am I clear about? Actually, I can iterate actually so many steps, but hope. Yeah. Okay. Is it okay or any questions? Is it clear? What we will do? So we're going to construct first with the matrix. I'll construct a graph, bipartite graph with cardinality of A equal to cardinality of B. Then I'll prove that it has a matching. When it has a matching means it is a perfect match. Perfect matching means I'm associating, right? That will give me a, so here it is not adjacency matrix, little different by adjacency matrix. Rows are indexed by A, columns are indexed by B. I'll explain you. So perfect matching will give one permutation matrix. Okay. That permutation matrix is constructed from Hall's-Maris theorem. That is the idea. Okay. That's why I introduced Hall's-Maris theorem in the beginning. Okay. Yeah. So then I use the permutation matrix to apply induction later. Okay. So for example, look at this. So this is a doubly stochastic matrix, right? How do you construct a graph? Okay. So one beauty is that we are using graph theory to prove things. Okay. Yeah. So we are constructing a graph using a matrix, right? It is also a nice technique, correct? Yeah. So at least I'm enjoying that. Yeah. Okay. So now what you do, so you take the row sums, right? Okay, R1 and R2. Okay, R1 is a row and R2 is rows only, sorry, row is like a vector, RICJ, right? Vectors. So how you are doing R1, C1. Why there is, I'll put an edge. R1 to C1, R1 to C2, R1 to C3, R1 to C4. Okay. Whenever that entry is positive, I'll put an edge. Okay, are you clear about that? R1 to C1, there is an edge because row 1, column 1, entry is positive, right? So like that. So here we have 4 edges, right? R2 have only 3, okay? R2 to C3, there is no edge because R2 to C3, rth row, third column is 0, right? Yeah. So now I will not give this proof. It is a homework or you can do exercise. Easily you can do. So you constructed like this, then this has a, this satisfies Hall's condition. That is the idea. Okay, you take R1, R2, then the number of neighbors n of s is greater than or equal to 2. That is your goal. Okay, but the further you can use that each row sum is 1, column sum is 1, like that. If needed, you can interchange rows and columns, right? Better to have something. Okay, not tough thing also, right? Each row RA has at least one neighbor in B. Okay, so further, why each RA has at least one neighbor in B? That also you know, right? So using all these properties, you can see that it satisfies Hall's condition. Once it satisfies Hall's condition, it has a perfect match. It has a matching. Okay, why it is a perfect matching? Because number of elements in A equal to number of elements in B, right? Yeah. So that's why you have a perfect matching. That perfect matching. So for example, R1 to C1, R2 to C2, R3 to C3, R4 to C4. I can take that. That is exactly the identity matrix. Identity working here, right? Yeah. Okay. So you can take another one if you want. R1 to C2, R2 to C1, right? R3 to C4 and R4 to C3. So you can see like that. So R1 to C2, R2 to C1, right? And R3 to C4, right? R4 to C3. So that is also permutation, man. 1, 1, 1, you put, I'll subtract that. I'll take minimum and all I do, right? That is the idea. So we done that. So I proved this part. Okay, is it okay, clear now? I'm not giving like a proof wise, right? But idea. Is it okay to all of you? Okay, thank you. Yeah. Actually, I'm not giving many applications. Actually, there is many areas, majorization, two vectors are majorized. Then if and only there is a double stochastic matrix. Very nice theorems. Actually, Singh Harn, he proved that every positive matrix I can similar to a, sorry, we can do some row and column operation, convert into double stochastic matrix. Many nice theorems are there. So, but I'm not going, but I want to tell one particular thing. We proved by using Hall's theorem this, but one can prove by using Birkhoff-von Neumann theorem, we can use this to prove Hall's theorem also. They are equivalent. Like that, there are total 8 theorems are there. Why? What is the reason for choosing this topic? There is a Menger's theorem, there is a Dilworth's theorem in Posets. 8 different parts of the mathematics, different results, all of them are equivalent. They're completely different statements, but they're all equivalent. One can prove by other. Okay, so in later, if time permits, we will discuss that also. Okay, so one of the reason introducing this topic is that one of you may be interested to look at what are all those 8, how to prove them equivalent, and a very nice thing. Okay, yeah, okay. So this is the book one can follow. I actually taken entire content from here. Non-negative matrices by Henry Mink. Okay, yeah. So publications, Wiley publication, right? And there are many other things you can watch and see, right? Kushraho. So this is my supervisor, Ikelal. He always says that Kushraho. Like whenever I talk to him, at the end he will say this. Yeah. Over to you. Any other questions? Anything? Any comments?
Yeah, thank you, sir. This is the wonderful lecture. We are also enjoying the lecture and lot more things, little bit things when we are solving the problem, we are not thinking about that. This is the truly think in online, we are also think parallelly. So thank you for giving this wonderful lecture. And students, if you want to, and I also welcome to all the participant to take part actively and asking the question and taking the answer all the question. Welcome and thank you to all. And if anyone have any question regarding this or anything, he is free to ask. Yeah. Any one of you, you can easily ask.
Okay, if there are no questions, you can raise hand. If there are no questions, we'll go for a photograph, right?
Yeah. Chaitanya?
Okay,
Hello.
so yeah,
Yeah.
so just me, I'll stop sharing.
Yeah.
You are taking the photo?
I'll take it, no issues. Yeah.
Okay.
I'll stop sharing. Okay.
Yeah. So participant, please switch on your camera and we are taking a photo.
Yeah. Yeah, Sakshi, where is Sakshi? Yeah, Sakshi, you can keep your, like, this is your camera, now you can put it like this. Sakshi, yeah, now it's fine.
Is it our Sakshi from last year Hamirpur camp student?
No, she's Yadav, I think, from
she's
some other state,
okay.
yeah, not from Himachal.
Yeah. Okay.
Okay, so let's take the picture. So on the countdown of 3, we will click the picture. So 3, 2, 1, smile. Yeah, thank you.
Okay.
Thank you, sir.
Thank you.
Yeah, Chaitanya, you can stop the live streaming.
Yeah, one comment.